Welcome to Dr. Jimmy's Applied Calculus, ready for Chapter 5. In Section 1, we're going to look at ideas of increasing and decreasing curves or functions. Very important in real-world settings. So let's look at a possible curve here. Y equal f of x. And suppose this is profit. So these kinds of curves visually taking maybe into boardrooms. Here's our profit. And so we see things that the board likes, where it increases and places they're not too happy with because it decreases. So usually, though, you get a little bit of decrease. We hope that in the end we're increasing. But they're different. This is one curve, but different places where it increases and decreases. Now, we would like to know where that's happening, a way of getting at that. If we look at increasing, we notice a slope, tangential slope is positive. If we look at decreasing, tangential slope is negative. So we can distinguish the parts where the function increases is going up and decreases by the slope being positive or negative. So we could say a curve, y equal f of x, increases when the derivative, so f prime or df dx, is positive or greater than 0, and decreases when this derivative, the slope at each point, is less than 0 or negative. So, to look at where is it increasing, where is it going to decrease, we end up looking at inequalities we need to solve. When is the derivative bigger than 0? When is it less than 0? So we'll digress slightly here and look at solving inequalities. Okay, that's what we need to do. We're going to solve specific ones' derivatives, but let's just look at general inequalities at the moment. So with linear inequalities, first degree terms or constants, we have standard ways to deal with that. So suppose we start with this, first degree polynomials or linear expressions. 3x plus 7 greater than 5x minus 3. So solving this is fairly much the same as solving equalities. We would subtract 5x from both sides, and subtract 7, and then divide by this coefficient of x, and get x compared to 5. The difference here, since it's not an equality, is when we multiply or divide with a negative number, you have to remember to switch the inequality. Negative multiplication changes direction, in essence. So we get a solution set of the values of x that are less than 5. If we move on to nonlinear, so for example, if we had x squared plus 5x minus 6 bigger than 0, so an inequality, how do we solve this? Well, we're going to first solve an associated equality. So take the inequality symbol, replace with an equal, solve the equality. So there may be different ways to solve at this point, but I think this one's not too hard to factor out. X plus 6 and x minus 1 is 0. We get solutions of minus 6 and plus 1. Now, the expressions we're looking at are generally continuous. And so no holes, no jumps. So the only way we can change as we graph from increasing to decreasing, or is to have a place where neither happens, or we get slope of 0. So solutions in the first step tell us the edges of regions that satisfy the inequality. So the second step is we're going to consider a number line with the solutions in the first step. 1 and minus 6. This creates regions or intervals. So we have x is less than minus 6. We have an equal. We have x less than 1, greater than minus 6. And then a last region, x bigger than 1. So, general inequalities, if it's not first degree, is we're going to solve the equality. This will break the real line into intervals. In this case, we have 2 solutions. Breaks it into 3 parts. So once we look and we determine those intervals, we'll pick some test values in each of the 3 intervals. Okay. The test values, I say pick them, is that there's no one correct pick. There's any pick in the interval. So here, let's make some choices. maybe in the interval minus 6 to 1, 0. Zeros, ones, and things like twos are nice, easy numbers to work with, so I generally pick those, but you wouldn't have to. So for a value that's actually bigger than 1, I'll choose 2. I need something less than minus 6, so at that point maybe 10s are easy to work with also. So I have a choice on each of the 3 intervals. I could have made other choices as long as they were in the intervals. Now, the testing comes by taking the expression x squared plus 5x minus 6. So this creature, we want to know x squared plus 5x minus 6. We want to know when is it greater than 0. So that's what I'm testing. I'm taking x squared, but now if I look at my one test value, minus 10, what happens? We get 100 minus 56. So we get a positive value. So, well, that's what we were supposed to find. When is this positive? So we determined that that entire interval containing minus 10 solves that inequality bigger than 0. So we just needed one test value. Now I'll move on and test the second interval. I chose 0. So 0 squared plus 5 times 0 minus 6, being minus 6 is less than 0. So this interval, x bigger than minus 6, less than 1, is not part of that solution. Although it does solve the other inequality, the less than 0. And then I tested the last interval at a choice of 2. So I get 4 plus 10 minus 6. It looks like we get 8. In any case, is bigger than 0 again. So x bigger than 1, and that was my choice of 2 in that interval, is another part of the solution. And so now I've run out of intervals, so I have some intervals that are part of the solution, others not. So the solution set would be x less than minus 6, or I would have to move over to x bigger than 1. So that's the general process. Solve the equality. It divides the line into intervals. Each interval, it's either strictly bigger than 0 or strictly less than 0. So in that way, I just test one point to discover the solution. Now, I'll move to another example. Two x plus 3 divided by x minus 2, less than or equal to 0. So we'll go back. We'll solve the equality. In this case, though, we have a little extra work. Because we have a discontinuity, possibly. If the denominator is 0, we don't get a solution, but we also, the curve has a discontinuity. So we have to consider division by 0 also. Now, when we set a fraction equal to 0, it's really the only solutions would be because the numerator is 0. And so we get one solution for a 0 of minus 3 over 2. We have a discontinuity if x is equal to 2. So, in the first example, it was nice and continuous polynomial. We just had to worry about equal to 0. We also have to, when necessary, consider discontinuities. So once we get past that, we take the values I found, which are just 2, consider them on a number line. I like to go ahead and graph it out. So in the correct order, minus 3 up to 2, I make my intervals are going to be x between minus 3 halves and 2. I'll have an x bigger than 2, and the set of values x less than minus 3 halves. We'll choose a few points. In the first interval here, it looks like minus 2 would suffice. 0 is in this middle one, and maybe I'll take 10 that's past 2. And so my third step is test those values. So I have my 2x plus 3 over x minus 2. So at these 3 test values, I'll substitute. So if I use minus 2, the value will be minus 1 over minus 4, which is positive. If I substitute zero, I get 3 over minus 2, and we're back to negative. Substituting can, we get 23 over 8, which is again positive. So for the strict part of the inequality, we found an interval where we get solutions when it's less than 0. And only on one interval. The other two are bigger than 0. So our solution set, well, we have x on the interval from minus 3 halves to 2. And then we have to put any solution, because it was less than or equal, any solution to equal, which was just the one endpoint minus 3 halves. 2 was not an equality solution, it was that discontinuity where we divided by 0. So we have this basic pattern. Solve the equality, also include any discontinuities, usually for us, division by 0 values. That divides the line into intervals, and then test each interval and pick the ones that give you the right inequality. So let's return to increasing and decreasing. So let's take f of x equal 2x cubed plus 3x squared minus 72x minus 15. So we have a curve. If we want to look at the values where it increases or decreases, we're going to look at the derivative. So in this case, 6x squared plus 6x minus 72. And so our step 1 is, when is the derivative equal to 0? We'll need to know where it's positive and negative to answer increase and decrease. So we start with where it's doing neither, it's just 0. And so we might solve this different ways, but I notice there's a common factor of 6. Leaving x squared plus x minus 12, and then that's not probably too hard to factor into a 3 and a 4. And finally we get 2 solutions, minus 4 and 3. But it's a nice polynomial, so no discontinuities. So we move on. We now have our values. We can consider them on a number line. Minus 4 to 3. So we have intervals x less than minus 4, x between minus 4 and 3, and x bigger than 3. The third step, choose test values. So a value in each of these intervals that we found. So I think minus 10 would work nicely, less than 4. Minus 4 to 3, fortunately 0 is a nice thing to pick. Bigger than 3, maybe I'll go to 10. Okay. So now I need to test our derivative. So 6 and then times x squared plus x minus 12. One of these forms I have up here. I think I'll take it with the 6 factor now. 6, we have x squared let's see, check, because it plus or minus x back here, plus x minus 12. So my first test value was minus 10. So I have 6, and this other part is 100 minus 22, 78. At that point, I can certainly tell that that's a positive value. The next test value I chose was a 0. So now we have a 6 and a minus 12, certainly less than 0. And then I moved over, and my last test value was plus 10. So we get 6, and then we get 100 plus 10 more minus 12, which I think is 98, certainly a positive number. So when I evaluate, a rough estimate might be enough. I just need to know, I don't need to know exactly what this number is, I just need to know positive or negative. So sometimes I might do a quick estimate, I know it's positive or negative. So here, what we found. We have positive slope, and where I tested minus 10. So that would be x less than minus 4. I also had positive slope when I tested plus 10. That was the interval x bigger than 3. I get negative slope where my test value was negative. That was the interval between minus 4 and 3. And then I get 0 slope, or horizontal, at those two particular values of the derivative being exactly 0, so the minus 4 and the 3. So this is what it told me about the derivative. This is then my interpretation back to the original curve and its slope. So I get positive slope, so this is increasing part of the curve on two intervals. On the interval in between, we would see the curve or the graph of the function going down. And then at the solutions to when the derivative is 0, we would have horizontal tangential direction.